first one we're going to start with. Remember that when it asks us to find the solution of the differential equation, our goal is to get to y equals at the end, right? That's the solution. On this one, and you'll see this in your assignment, it gives you some weird, like why they don't just put this in to begin with, but it says dy dx equals k times y if k equals negative 0.5. And then they give us some information off to the side, some initial conditions that y of 0 equals 200. Okay, well, the first part of it, dy dx equals, I can just sub that in so it's not as distracting. All it's saying is we've got a constant multiplier on the y. The reason they give us that problem is because eventually we're going to talk about a shortcut when the problem is of the format constant multiplier times y. The answers end up the same way every time, and if you have initial conditions and know the constant multiplier, you can actually skip a lot of the work. Not necessary, because you'll see that we can do the work here and get to the same answer. But we'll talk about a potential way to speed this up. We've looked at one like this before. We said that when it had a y to the first, as we move it over to the other side, we would divide by y. And that meant we were going to have an antiderivative of what? Natural log, which then eventually down the road meant our answer was going to have an e in it, right? We kind of talked about this before, looking at this a little bit closer. And again, we're going to have some specific things happening here to look at a shortcut. I do have an initial condition looking ahead. It's going to be that my y value is 200. So I know I'm doing my absolute value symbols around y. So our antiderivative on the other side, negative 0.5x plus c. As we would always, at this point, we have an initial condition, so I would plug that in to solve for the specific value of c in this problem that goes through that point. Then we have the natural log of 200 equals negative 0.5 times 0 plus c, and our c value ends up being the natural log of 200. Last step, solve for y. So I take my c value, I plug it back in where there was x's and y's, and I solve for y. We saw this one before when we talked about solving a logarithmic equation that I need to get that logarithm by itself, which it is, and flip to exponential. So it would be e raised to the, on both sides, so we'd have an e, oops, not e, a y equals e raised to the negative 0.5x plus natural log of 200. And then we talked about that because of our exponent rules from algebra, that we can clean this one up and give both of those exponents the base of e. That if the base of the exponent and the base of the logarithm are the same, we get that other number in the problem, right? So natural e raised to the natural log of 200 simplifies to 200, which became then our constant multiplier in front. And we get a solution of y equals 200 e to the negative 0.5x. So I want you to look at the answer. 200 e to the negative 0.5x, and look at the original information given at the top. Do you see a correlation happening? Okay. Our constant multiplier ended up being the coefficient of the x, right? Our value of y on the initial conditions here ended up being our constant multiplier in front of e. Does that happen every time? It does if this happens. First of all, it starts out in this format, constant multiplier times y. And the initial conditions is when x equals 0. Because if x equals 0, this term's always going to disappear, making c equal the natural log of whatever this equals, which will always end up in the same place over here, which will always simplify to the coefficient of e. Okay? So yes, it does. And if you recognize that, it can skip from basically here to here, going skipping all that. Now, if I forget this, it's not a big deal, because obviously we can get to the correct answer. But it is a rule in your textbook. If you were to look at it, this is where it came from, and that's how it was developed, is this law of exponential change says this. If you have something dy dt, something changing over time is what this was specifically for, of some constant multiplier times y, then the solution to it is y equals, and then y sub 0 represents the y value at time equals 0, or on our last one at x equals 0, at your independent variable equals 0, times e raised to whatever that constant multiplier was, times t, or times your independent variable. On our last example, that was an x. Okay, so this y sub 0 is whatever your initial conditions are. Like you saw in the last one, at time equals 0. That number right there is this number right here. Okay. Yes, which we're going to see in like one more page. Yep, focused all on our exponential growth functions today. You've been introduced, and he said, is this like PERT? Which we're going to see on, I think it's the next slide, or soon. You guys saw PERT before. It is an exponential equation, and that's kind of our focus here is exponential growth and decay using these differential functions. So try that on this next one. Try not to go through the work we just went through, but to rewrite your answer given the information. Try to skip the work part of it. And again, they separate this because it does have a name. It's your growth constant or your decay constant. It's your rate of change here, and your PERT formula would be your rate. Putting that into our formula, the solution to this would be y equals, our y sub 0 is 72, e raised to your growth constant times t or x. Ours was dx, so x. Questions? Okay. Sticking with the whole idea of exponential growth, exponential decay, you guys have been introduced to exponential growth and decay formulas, and actually what we're going to see on this page is not really calculus, but it is tied to what we just talked about, and you can see then the calculus development between your growth constant and finding that solution that we just saw on the last page. But you have two different formulas up here. One for our compound interest, which is the one on the left. And let me remind you of what those letters represented. A is your ending amount. P stands for principal. That would be the amount you started with. R stands for your rate, and typically rate is given to you as a percent, but the rate that you put into your equation needs to be the decimal equivalent of that. So whatever we are given, we divide by 100 or multiply, move our decimal 2 places to the left. N represents the number of times that your situation, money, whatever, is being compounded per year. Typical words that you hear for that would be monthly, 12 times a year, quarterly, 4 times a year, weekly, 52 times a year, daily, 365 times a year. But typically, I would say mostly monthly and quarterly would be the common ones. And then time represents how many years your money is left in whatever account it's talking about. And then the other formula you see is a lot of times referred to as your PERT formula. We use this one when it flips from being compounded at increments to being compounded what's called continuously. So as soon as the situation turns to a continuously problem, your interest being compounded continuously, we use PERT, where P still stands for principal. We then have a base of E raised to whatever the rate is as a decimal times the number of years it is left in the account. The next two problems we're going to look at, just kind of reminders of how to use these formulas. They're not necessarily needing anything that's calculus skills, but just remembering some algebra skills for this. If you initially deposit $10,000 at 5.25% annual interest, compounded monthly, how long does it take to triple? A little bit of interpreting happening here. You initially deposit $10,000. That would be your principal amount. So for the principal, I would put in $10,000. The rate is 5.25%, which means R equals 0.0525, right? We move that decimal 2 spots. Okay. N represents how many times per year that our money is being compounded, and it said the word monthly. So N, every place we see an N, is going to be 12. And then T is how long it's going to be there, and that's the question. How long is the question? So that's going to be a variable. But then it says, does it take to triple? Okay, well, if we start with $10,000, what's tripling? $30,000, right? So we want our ending amount to be $30,000. We solve this equation for T. Okay, this is where our calculators are going to come into play a little bit here. First of all, order of operations. I can divide by that 10,000 first. Get that out of there. But the rest of it's inside the parentheses, right? Which has an exponent. But I can put all this together that's inside my parentheses. So grab your calculators. 1 plus 0.0525 divided by 12 is 1 point something. Okay, and then again, we're solving an exponential equation right now, right? So exponential and logarithmic are inverses of each other. So I've got my exponent solved for. I flip to logarithmic now, so it'd be log base 1.004 of 3 equals the exponent, right? Okay, you either need to remember on your calculator where to type in your log base, or if you have one of those older operating systems, we're going to have to remember our change of base formula. So if you are an older operating system calculator type of person, your change of base formula says log of the inside number 3 divided by log of the original base, 1.004. Most of us can just hit our math button and go to, it's like bottom of that list says log base. Type that in, and eventually then divide by 12, because I want to get T by itself, right? How long does our money need to stay in there to get $30,000? A lot longer than we want it to, right? 22 years to triple our money. Any questions on that? No, it is not. It would be 1 unit of time. So like I can think of an example where it talks about bacteria's lifespan is whatever for doubles in like a week or something like that. So then their times are done in weeks. So it's kind of relative to whatever the situation is, what 1 unit of time would be considered. Value in 30 years is just knowing how to type that in our calculator, understanding what the variables are and what goes in for each of those. What is the value in 30 years means I'm just plugging in 30 for time. My answer is the end amount, right? Okay, well, if in 22 years, 23 years-ish, we're at 30,000, it's got to be a little more than 30,000, right? Something more than 30,000. You think 50,000? I don't think it's that high. 48,000? Any questions? Okay, not a lot of calculus to do with that, but just a reminder on our exponential equations here. But we do have a problem that does involve some calculus. And it's going to go back to that initial value problem that we talked about at the beginning. It says, so still talking exponential growth. Colony of bacteria grows in a laboratory. At the end of 12 hours, there are 5,000 bacteria present. At the end of 24 hours, there are 250,000 bacteria present. How many bacteria were present initially? Okay, so we have an equation that we've seen today that talks about the initial value, right? We said that in the exponential growth equation, y equals y sub 0 e to the k t. Y sub 0 represented the initial value. Okay, so if I can use that equation and figure out what y sub 0 is, that would be our answer. We know some of the points along the way, and sometimes it's easier to see them in table format than just reading them up there. At time equaled 12 hours, we had 50,000 bacteria, right? And at time equaled 24 hours, we had 250,000 bacteria, okay? And so putting those numbers into the appropriate places in your equation, these are t and y values, which would be here and here. So we would have like 50,000 equals y sub 0 e to the k times 12. Okay, well the problem is I still have, remember e is not an unknown, that's a constant, but I have an unknown of y sub 0 and I have an unknown of k. Well, when we have two unknowns, we have to have two equations, right? So that's why you'll see that I use this other one as well to create a system of equations, right? If I've got two unknowns, I need two equations. We've got options of how to solve a system of equations. Elimination, which is not a good option, don't pick that. Graphing, also not a good option, don't pick that. I would pick our third option, which would be substitution. Okay, so for substitution, I need to solve one of these equations for one of my unknowns, right? So if we go do that, I could like take this equation right here and solve for y sub 0. Can't I just move this, divide by that e to the 12k? Right? And that says that y sub 0 equals this, whatever this is. Okay, well if y sub 0 equals that, I can plug that in for y sub 0 into this equation. Question so far? Okay. And then we have to remember, again, how can I kind of simplify some things? These are two fractions, so we can multiply straight across the top, straight across the bottom. But I have two exponential terms with the same base. So similarly, if I were to have in the top of my fraction, like a 2 to the 5th, and in the bottom of my fraction, a 2 to the 3rd, can't I subtract and call that 2 squared? Right? Same base, I just subtract the exponents. It's the same thing we're looking at over there, is they have the same base, both base of e, I can subtract their exponents. Well, 24k minus 12k is just 12k, right? So it kind of looks weird because it's one of the numbers we already have up there, but that's all I'm doing is I'm taking this exponent minus this exponent. And we get an e to the 12k, which puts us down to an exponential equation that we can just solve. We need to get our exponential term by itself. So I would divide by 50,000. 250,000 divided by 50,000. Hope somebody just said 5. Yeah. Okay. Flip to logarithmic, right? It's an exponential equation. To solve an exponential equation, to solve for the exponent, we flip to logarithmic. Log base e, which is going to look like natural log of 5, equals 12k. Natural log of 5 is just some number, which your calculators will tell you now. divided by 12. And we get I don't know. Okay. Good so far? That was not the question. Okay. The question was not what is K. The question is how many bacteria were present initially. Okay. Don't make this more complicated than it needs to be. On this page right here, we have something that says the initial number of bacteria equals, it looks like y sub 0. Okay. See that equation up there? Right here. Y sub 0 equals. That's what it's asking us. How many bacteria were present initially? What does that equal? So all we have to do is plug 1.34 into that. A little more space, I think. It's quite a few. I don't know how many. What? 389. All right. Hope you took good notes on that one. You're going to see it again. Okay. So now you have kind of a path of how to follow. Any questions on that? All right. You guys have quite a bit to do here, and let me tell you about what's going to happen over the next couple days. You do need to finish up that worksheet. You have an assignment out of the book. Tomorrow, I'm going to talk about one problem in here to help you specifically with problem number 30 on that assignment, and then you get work time. Tomorrow, though, you are also getting your quiz back, and we'll have your reworks to do, if there's rework for you to do. Okay. But the other thing, and I know it sounds like a lot tomorrow, but tomorrow I'm going to open up again another AP classroom multiple choice assessment. It is going in Power School this time. There were a handful of us who did not meet the deadline and get that in by last Thursday at midnight. So if that doesn't happen this time, you will just end up with a 0 for that score. So make sure that we are getting on AP Classroom. You will again get that 1 week. So it'll be open through the Thursday at midnight 1 week from tomorrow. Okay. So get on there and get that done. All right. So you guys have, I don't know what time to get out of here today. 10 minutes.